Oh, yeah. So you don't use those for velocity. There's a kinematic equation. Because it's not going the same speed the whole time, you have to use a kinematic equation that uses acceleration and time to calculate your final velocity. And that's the V final equals V initial plus A times T, times plus acceleration times time. You see that kinematic? So let me show you in the book the kinematic equation. You know the initial velocity is 0. And from part A, you should know the acceleration. Oh, in part A, it says to calculate the acceleration. Oh, you don't need your final velocity. You can calculate this without the final velocity. Let me show you. Right. For horizontal motion, right here. No, wrong one. I'm in the wrong section. Gotta go find the right section in my book here. Where did it go?
Interesting.
Yeah.
Real quick, for part B, would I use the one that's y equals y naught plus v naught y times t minus 1 half g t squared? And then just solve for t?
Yep.
Okay. And since my initial velocity is 0, that first t that isn't squared is just going to go away, right?
That's correct.
Awesome. Thank you.
Where is that? Is it section 5? I don't know what it is. Let's go look at it here. Let's see. Yeah, I think it is section 5. Let's go to section 5. Okay. Hang on, I can't find my list of kinematic equations in the x direction. I'm totally lost. All right, I'll just do a search. Oh, here they are. Goodness, there they are. Okay. Oh, but that still just gives me just the one in the horizontal direction. That's really obnoxious. Okay, well, that's okay. I really want them all in the horizontal direction. Where is that? Oh, here they are. Okay. So here are the kinematic. So yeah, the third one down requires you to know the initial velocity v0, which we do know, and the final velocity, which we don't know. So that one's a little bit of a problem, but if you just go to the next one down, the next one only requires you to know the initial velocity, the initial position, the final position, which is the end of the table, right? Yeah, and the time. And then you have to know the time, and then you can calculate the acceleration. And then you can use that time, or you can use that acceleration in the previous one for the next part. Does that make sense? Okay. So as a quick review for number 9, part A, you need to find out the acceleration. You have the time, and you have the initial and final position, and the initial velocity, and this equation is great for that. For part B, you need to know the final velocity right before it leaves the table, and you know the initial velocity is 0, and you know now the acceleration and the time, so you can use this third equation here. Part C in number 9, you have to use, let's see if I remember what part C is. Yeah.
On part A, we're just asking for the find the acceleration. Is the v equals v naught plus acceleration times time still good, or is the other one better?
For part what?
For part A, what's that?
Yeah, in part A, you don't know the final velocity yet, right? You're still
Okay,
trying to
so
figure that out. You use this one. I would use this one for part A, because you know the time that it takes to go across the table, right? And you know the distance across the table. What's that? X naught is 0 if you just consider the edge of the table 0, yeah. Yes?
What I did was, I just said that the velocity equals distance divided by time, 1.5 meters in 0.5 seconds. So I just found that there. Is that all?
But no, because that gives you that assumes that it's moving at the same velocity the entire time. That gives you average velocity. But you need to know the actual final velocity because it's accelerating. So the acceleration is constant, but the velocity is not. And then, once you've got those done, then you use trigonometry to get the x and y components in part C. And then part D is where it gets a little bit challenging, right? In part D, they want you to calculate how long it's going to be in the air, and then how far from the table it's going to land. So how long it's going to be in the air is going to depend on its y direction motion, because it's going to be just like an up and down motion in y. It's just like throwing a ball up and letting it fall down. Even though the car is moving horizontally, remember those two motions are separate. It's the same as shooting a gun horizontally and dropping a ball, right? They're going to land at the same time. So this one, we take the y velocity initially, and we plug it into our kinematic equations for y. Now the kinematic equations for y are, in this book, a little bit different because they plug in negative g for their acceleration. But the thing that we have is we have the initial velocity in the y direction. We have its final position, which is going to be at the ground, and we know how high the table is, so we know its initial position. We can use the height of the table as our initial position, the ground equals 0 as our final position, and we want to calculate the time. So if we know initial velocity, initial and final position, and we want to calculate time, this is our equation again. We're going to use the quadratic equation again. That's going to give you two answers. You're going to have to choose the positive one, and then you plug that time with initial velocity into another equation of your choice to get how far it goes in the x direction. Now the velocity is going to be, your initial velocity for the last part is going to have to be initial velocity for x, because you want to know how far it goes in the x direction. So use that time from the y direction in the x direction kinematic equation for the last part of part 1. Did you catch it all? That's all right. That's all right. And today I have to leave at 6 o'clock. I apologize, but I have an appointment at 6 o'clock that I forgot about. So I do have to leave at a specific time. Does what? 0.8. How long is your table? And how long is it on the table? What's your time? Yep. How do I figure out what my own phone number is on my phone? Oh, I got it. Okay.
So you said using, to find that acceleration in part A, using x equals x naught plus v naught times p plus 1/2 a squared,
Because you know all that stuff in the x direction,
except for the
time, except for the acceleration. Okay. What else we got?
We're not sure what I did wrong on this equation. Because I was trying to solve that equation for A before I plugged any numbers in, because it's easier to do.
Okay.
And
So your V naught is 0, so you can get rid of that term. Your X naught is 0, you can get rid of that term. So it ends up being X equals 1/2 AT squared, right? Solving for A, you're going to get 2 times A divided by T squared. So A is 2x over T squared. Does that sound right?
yes.
Alright.
Okay, I still got the same business. Because the number that's popped out for me for acceleration is 12 meters a second squared.
Well, that's pretty fast. How long is your table?
1.5 meters.
Yeah, what's your
It's
time?
0.5 seconds.
Yeah, that's a little fast. So are you squaring the time?
Yep.
And so you're getting it's 0.5 seconds? 0.25? And you, one point what meters for your table?
1.5.
0.5 divided by 0.25 is 6, right? And then you're multiplying by 2, right? And so that is 12.
Is that right?
No. I don't think so. Did you get yours right, Leslie? Did you plug it in? You're on part C. Did you? How about your part A acceleration? Did you plug that in yet, or you just didn't? But you haven't submitted. I guess that makes sense because then you get other parts wrong. Right? That's another thing we need to fix about this program is should be able to submit each thing separately.
That's a problem.
Like if it's a blank, if it has a blank spot, and that shouldn't be hard to program. I'll have to talk to the guys about that, but it shouldn't be hard to program it. That if it's an empty space, if it's a blank thing, it just doesn't count it wrong. Doesn't count it as anything. I'll have to talk to him about that. That needs to be done that way. You don't know how to do what? Part C? This is the one where you're going to use trigonometry, sine and cosine. Yeah, so that's on part B. The number that you got in part B, that's what you're going to use for the hypotenuse of the triangle. And then you're going to calculate the x and the y coordinates, coefficients. Let's take a look at, let's see here.
You want me to come up there so you can see my work, see if I screwed something up?
No, I'm just going to look at your thing here really quick from my end.
Okay.
Look at Leslie's too here. So this is number 9, right?
Correct.
A. What did you have for part A?
For part A for my acceleration, I have 12 meters a second squared.
12 meters per second squared.
Yes.
And Leslie, what did you have for your part A? Yeah. And what did you have for part B? 1.4? Okay, your numbers are correct. Just so you know. Give you a little bit of relief there. And then Andrew, right? You go by Andrew?
Yep.
So your first one.
Is way off.
Oh, actually, it's not. That's not off. Let me see the.
12 is right.
Yeah.
Okay.
You just have a really high torque race car.
I want one.
Sweet.
I really want one now.
That is a pretty fast car. A wind-up toy that has 12 meters per second of acceleration is pretty intense. 12 meters per second squared.
Better not like go to early, otherwise it's like gonna fly out the window or something.
Yeah. It'd be the best Pinewood Derby car ever.
Yes. I was never particularly good at that. We always ended up like there's two brothers who were like super into the Pinewood Derby cars, and they would always have this new design, and I would just kind of copy whatever they did the year before.
So you're always a year behind their design?
What?
You're always a year behind their design?
Yeah. So I was working off the second best design, but
Well, I always knew how to make the cars fast, and my kids always did pretty well. But more importantly, we always made really cool looking cars. Like one year, Packer wanted his car to look like King Tut's sarcophagus. So we made a carsophagus instead of
Yes.
a sarcophagus. And it is awesome looking. We still have it. It's gold and it has the beard and everything. I mean, it's all carved so that it's shaped like it. It was awesome. So sweet. And it was the coolest car that year. And then Micah one year wanted a submarine. So we made a submarine with propellers on the back and everything, the periscope and the sail and all this cool. It was a sweet car. And that one had orange wheels just because we found some orange wheels and we wanted to use orange wheels. And we did some other really cool ones too. Trying to remember. Oh, we did a X-Wing fighter from Star Wars. That was a really cool one. That was tough to get the wing, because the wings, where are you going to put
it was
those?
so fragile.
Well, we made them pretty strong. We made them of balsa wood and glued them on. No, actually, we made them from wood that we cut off from the car and glued them on, but we had to make them super short because they can't impede the other tracks. But that one was a fun one too. Then we did a boat one year, a car that looked like a boat, and that one is actually our fastest one. That one won first place in every race it ever raced in. But I always wanted to make a two-piece car that had 8 wheels, and that separated in the middle, so that when you got down to the flat part of the track, the back part of the car would shoot the front part of the car up forward. So the back car would shoot backward.
Please tell me you're making a VW bug with a big 50.
Yeah, I mean that would have been sweet. The love bug.
Yes, that movie's good.
That is a good movie. But yeah, the original Herbie movies. But was that Herbie or the Love Bug? I think it was actually Herbie, the original one. But anyway, but yeah, that one.
Finished first and third.
That car would have been great because it is timed off the front end of the car. There's no rule that says the entire car has to cross the finish line.
Uh-huh.
So it would have been cool, but I never made it.
Technically, if you stopped like 2 feet short of the race, just pull the bumper off and throw it across the finish line.
Well, the idea was that the hard part of that design was figuring out how to trigger the explosion, because you have to trigger it when it goes level. If you trigger it before it goes level, it's going to go all crazy off the track. But if once it gets level, it has to trigger. So I was thinking if I have a pendulum on the top, and when that pendulum comes down, it hits a trigger. So it was still difficult to figure out. So anyway, someday maybe I'll do it.
We just made catapults in my class, and we only had a week to do it, but I wanted to try to figure out a way to trigger a spring once it got to the slot to push it farther.
Oh yeah, like the sling on the trebuchet, right? A sling on a trebuchet does that. We did. I've done 3 different varieties of trebuchet. I've done well, I didn't actually build it, but some students of mine did. They built floating arm trebuchets. Those things are super compact and they throw so far. I saw one of those that was only 6 feet high and it threw a 10-pound pumpkin 380 feet.
Oh, wow.
Just insane. And then we built a trebuchet that was 17 feet high. It was 12 feet high at the axis and 17 feet high to the top of the arm, and then it had a sling on it that was like 7 or 8 feet long. And that thing threw about 380 as well. And then I did a fixed arm trebuchet, but then I actually built a type of Merlin trebuchet, which is one that has a cantilever wheel on it. And that one, the weight that was pulling on the trebuchet was actually pulling on an egg-shaped cantilever wheel. So that at the beginning of its motion it has low torque, but at the end of the motion it has high torque. So it starts off nice and slow when it needs that slow movement, and then at the end it's just ripping that thing around. And it ripped it around so fast that the trebuchet over-rotated and broke itself. But it threw a basketball, not a pumpkin, but threw a basketball pretty far. Yeah, that was good times.
Mr. Daly,
Yes.
on part B, we're figuring out the distance.
Part D.
Yes.
Okay.
I found the time using the Y formula.
Yep.
But I use kind of the corresponding X formula since I know everything.
So now that you know the time, remember in the X direction, this car is moving at a constant velocity in the X direction. So if you know the time, you can just use distance equals velocity times time in the X direction. Right?
Okay.
It's just like shooting the bullet out of the gun horizontally. We're shooting at an angle this time, but we know the time, so that's no big deal. If you know the time, you're good to go.
So
It's like the experiment, instead of dropping a pin to see how long the bullet's going to be in the air, you throw the pin up to see how long the bullet's going to be in the air, right? Because it's the same independence of motion. The horizontal is only dependent on time, not on the angle. For part D? For part D, did you get your time in part C? Did you calculate the time? So once you calculated the time, you can just use the distance in the x, so x equals velocity times time. And you use the x velocity, so it's x equals v sub x times time. In part D. X equals v sub x. So it looks like this actually. It looks like x final equals x naught plus v x t like this, but your x naught is 0. So this is the equation you get. I am going to download the Zoom app from my iPad so that I make better drawings. That whiteboard on this thing stinks. I have all these iPads I bought several years ago and I hardly ever use them. I need to start using them.
if you want to get rid of them, I'll take one.
We've done a bunch of experiments with them. I have them all encased in those really heavy-duty rubber cases, so we can like drop them down the stairwell or whatever, and record the acceleration and do all kinds of cool stuff. But I just haven't had time to use them too much. I've used them a fair amount, but not a lot. I think I have 6 of them.
No, I did not find the time.
You didn't get the time?
No. I thought you said from first year and I didn't realize it was.
So the time, you have to use the quadratic equation in the y direction. So that's this one right here. This one right here.
Hey, Mr. Daly, on part B where it asks for the total displacement, is it asking, so we would set it up like
It's when it's asking for what?
so it's saying, okay, so you started with your table, you've shot the car off, or it landed, and it wants your total displacement. So we set it up like a factory.
Oh, yeah. So it's the total displacement is from the beginning of the end of the table where starts, the left end of the table, all the way to the landing point, and just set it up like a triangle and find that vector.
Okay. One thing, it gives us like the height of the table plus the ramp. So how are we going to find that height of just the table or just the ramp?
Good question.
Because when we used the Pythagorean stuff earlier, we knew the angle of it, but we don't know any of it. We used velocities with Pythagorean. We didn't have the actual size of the ramp.
Let's assume that the ramp is negligible in height to the compared to the table.
Okay, so I'll say 1 point, on mine it says 1.9 meters for the height of the table on the ramp. So just use that as my height?
Yeah.
Okay.
Why is it that I cannot get this visitor network to work? I can't gonna get anything to work here. It's ridiculous. This came up.
And since since it landed below the table and off to the right, we would pick the arrow that's pointing down towards the right, correct?
Yep.
Okay.
What was I trying to find? You said it was the what was I trying to find?
In part D? In part D, what you're trying to find is the distance it travels from the table. Well, you're trying to find its the horizontal distance from when it goes off the table and off the ramp and lands on the floor, right? That's the X. Yeah, that's right. So you're looking for X. No, you're calculating X in part D. Yeah, so you already found the time, right? Oh, so you're, okay, so you haven't found the time yet. I thought you'd found the time. Sorry. So to find the time, you're going to use the same equation, which is this one right here. T. Trying to calculate T. No, the final Y position, you know, it's 0. It's when it hits the ground. And the initial Y position is the height of the table that they got there for you. Sorry, I must have confused you. Ah, fine.
Um,
So the time is zero.
Mr. Daly,
Yep.
I got part B wrong, and I just reran all my calculations, and it still came out the same.
Zero.
You got. Okay, what was
It's continuous speed, right?
So you got 0 for your time? That's it?
Because it was 0 divided by 0.406 minus 410.
Where did the 0 come in? That shouldn't have been
That
there.
was what
So this is your equation. Y equals y naught. So you have initial y naught, right? What's the height? This is the height of your table. What is that?
oh, I had 0 for that. That's fine.
So your final y is 0. This one is 0. But this one is the height of the table. Then plus v naught t plus so on and so forth. Okay, what was your question there, Andrew?
So on part D, it says I got the time wrong, and oddly enough, it says I got the unit wrong too. I feel like it's just a format thing or something. Because for my unit, I put in seconds to spell out the word.
Uh-huh.
Should I just put S?
For time?
Yeah, for the, on part B, you have to scroll to the right to see it.
Come on, you dumb nut. Looks like it gave me it if I just put an S.
Okay.
Yeah,
Is it alright if I message you about that?
yeah, go ahead, anytime.
The other thing was about my actual number for time,
Yeah?
because I used the equation that you told me to, basically kind of the same one there. And
Yeah.
I just reran the numbers to see if I did something wrong.
What did you get?
What I have is 0.623 per seconds.
Number 9. You have 0.6 what?
0.623.
You should have gotten 2 answers, one positive, one negative, right?
Well,
Oh, because the initial velocity. No, your initial velocity has a value, so it's not going to be 0.
oh, that's what I did wrong.
Yeah, you have an initial velocity.
Initial velocity is 0.
Your initial velocity in the y direction is not 0. You have to use
your
the
answer from the previous problem.
yep
right?
v sub y from the previous problem, exactly.
No,
That's
I
what I did
had
wrong.
a negative 1.6.
For your time?
No,
Oh, for your distance.
for my why not? I had 1.6, so I moved it over. So it's negative 1.6. And then I had square root it, so it doesn't work. It's square root.
So your y, so here's your table, right? This is you're calling this your y naught, 1.6, right there, that height. And you're calling this y final equals 0, right? And so if it's going from here to here, and that ends up being a positive, this is a positive in this direction, that means your v naught in the y direction is actually negative because Well, no, sorry, your V naught is positive, right? So you got that correct, right? But then over here, you should, did you have the minus 1/2 g t squared?
I use acceleration.
Yeah, because remember in the y direction, the acceleration is negative g. So the negatives will take care of themselves there.
And gravity is -9.8, right?
Yeah.
Meters per second squared.
That's right. Don't feel bad though. I mean, everybody has missed this problem a lot. This is a difficult problem. There's no doubt about it. There's just a lot of parts to get things wrong here. A lot of easy ways to get this wrong. And that's part of what we're teaching you here is methods and patience for solving complex problems. And this will serve you no matter what you go into. You'll learn to map out a problem very carefully and go through it step by step and do what you want to do. Okay, now I can download the Zoom app. Minecraft. 0.6 seconds does make sense. Yes. Did you have your original what's your V not Y? Well, it shouldn't be 0 because remember it goes off the ramp, so it has some initial velocity upward. In your previous section.
I did the same thing.
Yeah, he did the same thing just a second ago.
I did the same thing.
Because remember in the previous part of the problem, it goes off the ramp and so it has some upward velocity. That V0y needs to go right in there. Right? Believe me, it gets better. This is the worst of it. Well, there might be something in the next chapter that's equally bad.
This is actually my final velocity for part B.
Yes.
That's why
Yeah, your final velocity, but you also remember you resolved it into an x component and a y component. For this, you only want the y part of it. Remember the previous part? You did the trigonometry with an x and a y? Yes. Yeah, V0y is the thing you want in this equation. And that's why we label them so specifically.
Oh, this is from part B.
So that's part.
Actually,
So,
from part C, not part B.
no, that particular velocity you want from part B. That's the number you bring down from part B. But in part C, you calculate V0y, which you're going to be using in part D.
This is the
Yeah. Yeah.
So I didn't need to. So your initial velocity, since it's going off that ramp, you're using the y formula. You use your velocity for y. Like in
Yeah.
part C, we found the velocity for y when it's about to go off the ramp.
Yep.
And that's what since we're saying the distance or the time from when it
For it to go up and then fall down
when
again.
it goes off the ramp when it lands, we use that as our initial velocity.
That's right.
Okay, that's what I was doing.
Because you're just doing it in the y direction. Am I connected to anything? Finally.
Mr. Daly, I had a comment. When I was plugging in, when I was trying to find my time using the quadratic, under the square root, I had a negative.
Well, did you, so in this equation, did you put in the negative sign here?
Yes, I did.
Did you put it in here as well?
Yeah, so there's,
Remember, we talked about this a couple times. In this book and in several books, they actually have already put the negative in for you. You don't have to put in the negative here. Right?
I didn't miss that part.
oh my gosh.
Congratulations. That's why their equations are different in the y direction. With that negative g in there, they already put the negative in for you. So you can just change that negative under the thing and be good.
I've never had such a problem in any class in my life.
I'm sorry?
I've never had such a problem in any class in my life.
This is, I can tell you right now that for most students that take this class, it is the hardest class they will ever take. And that includes many engineering students. Because it is very, very difficult. It doesn't include electrical engineering students. And it doesn't include mechanical engineering students. I'm sorry, but you're going to have harder classes. But you'll get used to it. You'll get used to the intensity of it. Well, the beauty of it is that once you get through this class, you feel like you can do anything, and you really can. You literally, if you get through this class with a decent grade, you'll be able to take any class on the planet. And really, that's how they treat the students after they take this class in engineering and physics. Once you get through this class, they're like, okay, you've arrived, because 50% of the students who take this class fail it. 50%. It's a 50% fail rate across the nation. It's that bad.
I'm not liking my odds here.
In my class, it's higher, and in community colleges that are smaller, it is quite a bit higher. My classes have usually about an 80% pass rate or more. So sometimes I have 100%. I think this last year, I don't think I failed a single student. So, but the thing is that it's all about time. You have to spend the time on it, and I have the time to spend with my students. Most teachers can't spend time with all 200 of their students. So it's a little bit harder. And it's also a way that universities weed out the ones who aren't going to work hard. Because that's really what it comes down to, is can you work hard enough to get it done? And I know, because the first time I took this class, well, this class I made it through okay, but the second semester of this class really killed me. And the first time I took it, I had to drop it. I couldn't take it. It was just too much for me. And so I took it, so I went back and took it again. And I had been gone from college for 4 years at that point, so I hadn't taken anything in a long time. And that's one of the biggest reasons I was struggling with it. But I came back and did it again the second time, and got an A in it. So it's just you got to put in the time. It takes a lot of time.
This is why I dropped chemistry because I could not. I was doing
Because you were taking both at the same time.
I didn't know the first 2 weeks and the last week. So.
Yeah. I kind of thought that was a little crazy to be taking chemistry and physics over the summer. But yeah. Well, even then, chemistry is a tough class too. I don't think it's nearly as hard as this class. Chemistry was easy for me. If I didn't like it at all, but it was easy. I didn't get a good grade because I never went to class. I would just show up for labs and take exams, and then didn't do anything else. But I just never liked chemistry. So it's just the way it is sometimes. I think that both of you have this problem down. It seems like you're understanding this problem and you've got the right things going. I would probably not waste any more time today on it. And maybe we should move on to another problem. Work on another problem.
I want to get this thing done.
You can't? What do you mean erase everything you've done?
Like if you don't submit it for a grade and you go to
Oh, you mean the numbers you've typed in it will erase? Oh, just write them on your paper. And then don't submit. Does I can't remember, does this one have a save function where you can save your work? Okay. That's another thing we need to add in. But, so here's a question for you, since you guys are my guinea pigs. If you don't have to pay for a program like this, how important is that to you compared to paying, say, $50 a semester for the program? You still wouldn't have to pay for a book, but the other program that I use, how much is it? $30, $50 for WebAssign? Do you remember?
I can't remember. Complete disclosure, I haven't signed up for it yet.
Oh, that's fine. There's another one out there that I think is actually better. It's a better program because it's been around longer and they have paid programmers that are doing it. It's not just volunteers like me and whoever else is doing this. It's paid programmers and they have it's a very good interface. The downside to that one is it's harder for the instructor to put things into it. This one I can put a lot of things into it and change a lot of things on my own. But the upside is that it has the feature where you can save things. You can try out the problem before you do it without losing points. Like it'll give you a different version of the problem that you don't lose any points for doing. You can practice it. In other words. So would it be worth $50 to do it that way? To have extra amenities and make sure that it's okay. So you're not sure about that. And I'm still trying to decide if $50 a semester is reasonable for everybody. I know some students that I've had couldn't pay it, and even $50 was hard for them. But some students are just like whatever. You know what I'm saying? I preferred not to spend any money in college, but I had 5 kids while I was in college. So, well, my wife had them, but I was
A little awkward if you have.
I was working to pay for them. So I was working full time and going to school. So $50 was everything to us. That was a week's worth of groceries, almost. Oh, let's see if this works. Zoom. All right. I'm sorry, was that a question for me? Part D? Still on number 9 here. Part D. And what about it? So your X, because you're trying to calculate your distance now that you have the time? Okay, so your X naught, you just consider it to be 0, because all they want to know is this distance here. So consider your beginning point to be 0, and then they want to know how far you go to this point. So that would be your X final. Your final velocity is the same as your initial velocity, but you shouldn't need that equation. The equation that you need for the x direction is just this one. It's very simple. It's actually this one right here, right here. That top one will do it for you. Velocity times time. Velocity in the x direction times time equals your final distance, and that's all you need. That one will do it.
So on the second attempt, still didn't get number down, right? After we were
Which part?
B, time. And that's the part that I feel like is messing me up because I feel like when I did that time wrong,
Yeah, if you get the time wrong, everything else is wrong too.
yeah, everything else out, my units are right.
You got the seconds down?
Yeah, I changed it to an S.
There you go. Okay, let's see here. Let's take a look at what you got. Nine. What am I doing here? Number 9. So you're looking at it's part D that you're.
Yep, my time specifically.
And you put in.
0.386.
Oh, that it should have gone up, not down, because. So when you did it this time, did you get 2 answers in your quadratic?
Yeah.
And that was your positive one?
Yeah, the other one was negative 9.852.
9.8?
Negative 9.852.
Huh. When you calculate the time, you should get 2 separate answers because it's a quadratic. So when you plug in your numbers into here, you should get a number right here. This should be 0. You'll get a number here. You'll get a number here because that's not 0. And you'll get a number here, and you'll end up with something that looks like a number times t squared plus a number times t plus a number equals 0, which is a quadratic equation that you have to solve using the quadratic formula. We call this first number A, and the second number B, and the third number C, and we say that t equals negative b plus or minus the square root of b squared minus 4ac. So that quadratic formula, right? Well, that's 2 times A. And then when you do that, because of the plus minus, you're going to get 2 answers. What did you get for the time?
I put my other time in for the T.
The other time, this is how you should have calculated that other time.
No, the time that I had before at the very beginning, I used that for the T.
Oh, the one that they give you in the book. Yeah, that's not the correct time, unfortunately. So you have to calculate that time in part D. That's the first part thing you calculate in part D. 0.386, it should be bigger than the last one you calculated. Because the last one you calculated was calculating going straight off the table. So something is wrong in your quadratic. Let's take a look at that.
Mine? And this part, the initial, what I'm using is the initial velocity. So this is where I remarked it over here.
That is, oh, so this one.
Yeah, this one over here. And the A is this.
Okay, so this is one thing that's going to be wrong. No, it's not. That's right, because it's positive. So because it starts going that way. So it's positive. That's in here. That's correct. Square. You can minus the there, correct? So you can cancel. This is all over 2A, not 2C. The other one over 2C. Oh, no, that's it. But you have it as a positive, it should be negative. So that's 4.1 should be negative. That, all that does is changes the sign of everything. Which means that all it does mean the other one's correct, but this one is incorrect value. This one is incorrect. It should be
see that.
There's something, I'm not sure exactly where that, it looked right up until then, so.
Time, start on the first sheet.
That's what I never wrote earlier.
Let's go. And if you want, we can meet again tomorrow. I'm available tomorrow if you guys want to do it again tomorrow. Tomorrow is a little bit more difficult because no, it's not. They used to close the building on Fridays in the summer, but I don't think they do that anymore. So I think we're good if you wanted to meet tomorrow. It's just up to you guys.
Okay.
I have to plan a campaign.
You have to do what?
Plan a campaign.
Plan a campaign.
Girls safe.
Yeah.
Fun for you.
And I just really start on the next 2 weeks of
I'm gonna keep working on that, because I feel like I know what I'm doing, it's just somewhere I'm doing, you're right. I'm doing the math somewhere wrong, but I get the idea.
Yeah. Getting the algebra correct is actually one of the harder things to do. Just working out the details is hard to do correctly. It takes a lot of doing. So. Let's see if I can get this down here. I'm trying to connect my iPad to this. Topic, join from MacOS, iOS, or Android. Meeting ID. That's the 1, 2, 8, 1, 6, 1. Hey, I have another participant. I'm participating in my own meeting. It's kind of obnoxious. All right, let's try this here. Choose Wi-Fi network. Zoom, Jared's iMac. Can't see it. Okay. I like it.
Hey, Mr. David,
Yeah.
I'm looking at number 12. I'm trying to think through it and go like, okay, what do I know? What?
Number 12.
Yeah.
Hold on just a second. I'm just yeah, another time. Okay. Number 12. Nope, this one. Nope, that's not one. Chapter 3, number 12. Okay?
Okay, so we're trying to calculate distance, right?
So did you get the first part already?
No, I don't know. Would that just be 45 degrees? Or?
It is, remember that, and that actually comes from that idea of the symmetry. Remember when we shot it at 30 degrees and we shot at 60 degrees and landed at the same place.
So 40, okay.
And 45 is the only place that has its own complement, so it will always go the furthest at 45 degrees, as long as there's no air resistance.
Yep, and it doesn't say anything about air resistance.
That's
so
right.
I'm assuming that there isn't any.
That's right.
And it says during its flight is the speed the least, so that would be at the top, right? Because it's at 0.
Because its horizontal speed is the same the whole time,
Mm-hmm.
but its vertical speed is 0 at the top. So when the total speed of the overall velocity vector, in
It's
other
going
words,
to be the
is
least.
going to be the sum of those two. So it's going to be the least when one of them is 0, when the y is 0.
Okay.
Right?
And then for at what speed will it hit the ground?
Remember the symmetry. If it's launched from the ground and it hits at the ground, what's the symmetry with the
Oh,
velocities?
we go on 20.
It's
do I
the
need to go
s-
negative 29?
It's the same speed. Remember, speed doesn't have a negative or positive. Only
okay.
velocity does.
So it's
So it's
just,
the same speed,
so,
but it's just a different direction.
okay. So when it says speed, even though it says v equals, it's asking for speed, it isn't asking for a direction.
That's right. And that's when we talked about how in the book, if they're talking about the vector, they bold the letter. If they're talking about the scalar, they just leave it unbolded. So speed is v, whereas velocity is v bold, please. Or v with the arrow over it or whatever. Confusing? Absolutely.
Mhm.
But they have a lot of things to keep track of.
I knew that the 45 degree angle was the best because I had more than I was thinking I had.
That's right. Technically, if there's air resistance, though, it's more closer to 30 degrees. 30 degrees or 35, somewhere in there, 37, because you want to shoot a little more forward so that you can counteract that air resistance a little. But the funny thing is, the faster you go through air, the more air resistance you have, because air resistance is dependent on your speed through the air. So,
That's why even if you put the largest engine in a sedan would go far, probably have less air resistance than a semi-truck.
yeah,
And thus would go faster. I'm looking at a problem, number 14, where it talks about the velocity to tell you whether the acceleration and velocity is going up and down at various points. He's throwing the ball up. So as soon as that ball leaves his hand, it's accelerating down, isn't it? Because gravity is after it. So the answer would be the same. Right? Gravity is accelerating it down the whole time.
that's right. For any projectile motion, and remember the projectile motion, the definition is that it has some initial velocity, but it's not being accelerated in any direction except downward from gravity.
Okay,
So-
and then the rest would be fairly self-explanatory. Where
Yep.
as he's throwing it, the velocity is up at the top, the velocity is none, and it's coming down from the cliff, the velocity is down.
Yep.
Awesome. See, this part that doesn't have, never thought I'd say this, the part that doesn't have the math, it's the one I'm doing better than.
It's
So-
up, down, down.
Yeah, for the velocity, right? The acceleration is always what?
Oh, it's really positive.
What is pulling the ball? What's the only thing pulling on the ball? Gravity is the only thing pulling on the ball, right? So that's the only thing that's causing the acceleration. So it's always down for the acceleration, whereas the velocity changes its direction. And at one point, the velocity has no direction, right? Where does the velocity have no direction? You just said it. At the top, right? It has no direction at the top. Because it's just zero. I can't tell you how many math majors I know who used to be physics majors. They started as physics majors because they said, I love math. And then they got into physics and they're like, I don't like math this much. So they went to be math majors because it's easier to be a math major than it is to be a physics major.
My math teacher, she's actually she's my husband, but she is really good at math. And I had to learn physics at the end of the year this year because she wanted to put it in some
Yeah. Yeah, when you go into physics or engineering, most engineering, not all engineering, but most engineers and physicists have pretty much a double major by the time they're done. They have to take, if they want to get a major in math, they have to take a couple extra math classes in the math department. But that's it. I never did it because I hated being in the math department every moment I was there. So and I was paying for my own schooling and working full time during school and had kids and everything. So I just didn't go through but my first class, and my first math class in college was a 300 level math class. That was the first class I took. And, after that, I only took 2 more math classes. I only took 3 math classes the entire time I was in college. But they were all 300 and 400 level math classes. I never went below that because there was just no need. I've already taken everything else, And so it's very common to have a lot of crossover there. Well, a lot of people that leave physics to go into math, and a lot of people that double major from physics to math, and engineering to math. In fact, it's actually less common in engineering now because the engineering departments all over the nation are deciding to not have their students take any math classes anymore. They teach them all their math in their engineering departments because they don't like the way the math teachers teach it. They say, well, you really know math, but you don't know how to do anything with it, And that's really the problem, and that's the problem with math in general right now, is that we have this whole new crop of math teachers coming up who have never used math, even though they're math majors, because we have this pure math major going on, and they've never used it for anything. They just teach math. That's all. Some of them have never even majored in math. Really, they've only majored in teaching math, and that's a problem because you don't know what it's used for. If you don't know what it's used for, you can't really teach it properly.
Well,
Yeah.
it's like, my dad's
So the newer math teachers these days we're struggling as they come up.
it's teachers, no offense,
Yeah.
like, you have more experience with it, but like teachers as a whole, like my personal finance teacher learned business education.
Yeah.
My dad's a financial advisor, so as I'm taking the classes, like, okay.
Yeah, and your dad's changed things.
No, this is how it works in the real world. It's just a brother.
Yeah, and that's really what we want in college instructors and college professors. At the community college, we're not professors. We don't have that rank. That rank is something you have to earn at a university. But we are college instructors, and we should have experience in our field. We should have some real world experience in our field. But where do you get math experience? It's hard to get. You'd have to go work for an insurance company as one of their insurance. What they call them is what's that?
Actuary?
Yeah, as an actuary. And because actuaries, what they do is they work the math of ripping people off with insurance. Actuaries also work in Las Vegas. They're the same people. They're the same, and they have the exact same job description, the exact same education. They work on figuring out how to rip people off using games, and because that's all they're trying to do. They're trying to make it so that you pay enough money, that everybody pays enough money that they make a profit all the time, no matter what. No matter what's going to happen in the insurance or what's going to happen on the game floor, the casino or the insurance company always makes money. And that's what they do. That's their whole job. But besides that, there's not a lot of other math jobs out there. There are some math consultants, but most of them are consulting in engineering or computers. And so they have to have engineering and computing backgrounds as well. And all of the great mathematicians of all time, every single last great mathematician of all time has either been an engineer or a physicist. Every single one. There is no such thing as a great mathematician who hasn't been a physicist or an engineer. because they know how to use it and they know how to do things with it. But it's a tool for us and it's a theory for mathematicians. So it's a little bit, there's a little disconnect there. Just kind of like having a person who's learned how to teach business but has never done business. You know, it's kind of, there's a disconnect. They're just, the real world experience doesn't connect their knowledge to anything, so, because they don't have it.
Mr. Bailey,
Yep.
on number 15, I know you kind of gave us the formula for figuring out the time, and then for distance, it's just speed times time. In the formula, you give us t equals the square root of 2 y naught over g. G being
That's the
gravity.
formula we figured out from here, right?
Yeah.
So we take this formula. Let's check it really quick. If we say that our initial height is the height of the table, that's why not. Our final height is 0, which is the ground where the cannonball lands, right? Then our initial velocity in the y direction is 0 because it's shot horizontally. This goes to 0. Then this is the equation again, right?
Yep.
And we need to solve this for t.
Yeah.
We're solving for t. So we could add this thing to both sides and we would get 1/2 gt squared equals y naught, right? Divide by g, multiply by 2, and this is a t squared, right? And then take square root of 2y naught over g, is that what you said?
Yeah, square root of 2 y naught over g, but
Yeah.
g, gravity's going to be negative.
No, the negative's already there,
Oh,
remember?
gotcha.
Sorry.
I wasn't sure if that still applied once we fixed it or not.
Yeah, it does. All right.
And on number 15, it has more than just 5 slots for answers, but I'm pretty sure there's only 5 candidates.
1, 2,
There's 6 candidates.
1,
There's
2,
11 slots
3,
for
4, 5, 6, 7, 8, 9, 10, 11.
And there's only 6 candidates.
Oh, but in between each answer, there's a greater than, less than, or equal sign.
Gotcha. That makes sense.
Or, yeah. So if any of them are equal, then you have the option of putting the greater than sign.
Okay.
Yeah, I was confused by that at first too. It was a little weird. But. I'm sure if you log in iPhone, choose Wi-Fi or select parent. Visible, select parent. You still have questions on that one, there, Leslie? Remember that for this one, you have to calculate the time for each one of the cannonballs and multiply it by the speed of each one. So each one you have to do separately, and the one that goes the furthest distance with those is your last one you put in, right? The first one I think this is number 15, right? So the one they wanted, no, the first one is the farthest, right? So the first one that you put in is the one that goes the furthest, A, B, C, D, or F, and then if it's equal to the next one, you put an equals. If it's greater than the next one, you put a greater. That means that you probably got the second one wrong and maybe the rest of them right. Right? Tell me what you did. Let's see here. We can do this. I can look at yours really quick and see what I've got for you. So tell me the letters that you have in order. So A, E, B, C, F? D, C, F? Okay. Yeah, your second one is wrong. It's not F. Your second one, sorry, it's not E. Yeah, sorry. It's not E, your second one. I'll give you a clue. You have everything right after the second one. Your order is completely right after the second one. Because they're all out of order, because the second one is wrong. So your second one should be your third one. There's another one. The only one that you have out of place is actually F. So recalculate F, the F cannon, and see what you get. Oh, so what is it now? Okay. So that's probably your second longest one, right?
Holy crap. That did not go well. Wow. It says I got all of them wrong.
So which one? Tell me what you've got so far. If you got them all wrong, then maybe your first one is wrong and the rest are right.
Maybe. So I got F, B, E, E, C,
F, E, B?
A. F, football, basketball, dog, echo, Charlie, alpha.
Okay. Where is it? There you go.
Do I have in reverse order, or did I get something wrong, or what did I do?
So you did F, B, D, E, C, A. Yours is all out of whack. Did you do something goofy?
Yes. In that original formula,
Yeah?
y initial,
Yeah.
I was putting in my velocity for some reason.
Yeah, because yours are all out of whack.
Oh yeah, yeah, they are way out of whack. Wow, that was really stupid.
These things happen.
Once again.
So did you get it right this time?
Oh, I hate when it happens. I just typed in the stupid calculator wrong.
Calculators are a big pain in the neck, and in fact, this is the class that is well known as the last class that physicists use calculators in. Because they get so tired of calculators that, and literally during the same time of the year, in most physics departments, you're learning how to use a computer to do your calculations. So you're learning computer programming, and by halfway through this semester, every single physics student has figured out it's easier to do it on the computer because it'll save everything for you, and it can do the calculations all at once. You don't have to, do one and then do another, and then you only have this tiny little screen. You can type it all out, and it'll do all these calculations for you. And then by the end of that first year, everybody's got these fancy calculators they bought to start college with, and they never use them ever again, except to do like little things. Oh, it's 48 times 72. Okay, whatever. They use them for arithmetic. They don't use them to do great big calculations anymore. And every school has their favorite program for doing their big calculations. The school I went to used a program called Maple. Lincoln uses Mathematica, which is actually a bigger program, better program. But yeah, you come to a point where you're just like, I hate calculators. Because there's so many easy ways to mess up what you're doing.
You would be correct. Like substituting the velocities instead of the height.
Yeah, and see, like in something like Mathematica, all you can do in Mathematica or MATLAB or Maple, you can just type in the formula and then type in a list of velocities and say calculate all of them. And it'll just plug them all into your formula and say this one, this one, this one. And you can do like 900 calculations at once and you're just like, done. But we have to make you suffer.
Yogi arrow.
I actually have several high school students that take my MATLAB class during high school. And they discover this early. And so they go on to take a physics class in high school and they're like, man, that class was great. I know all these calculations. I mean, MATLAB is designed to do parallel calculations thousands at a time. So you can type in one formula and type in 1,000 different things you're going to plug into it, and it'll do it in 5 seconds or less. Well, it'll do it in a second or less, really, as long as it's not too complicated of a formula. But yeah, it's not that hard to use, really. It's just you have to learn it. You have to take some time to learn it. But yeah, it's usually the first year they teach you that so that you can get away from your calculator as quick as possible.
I don't even know how to use my graphic calculator.
Yeah, I never had one. I borrowed one from my brother, and the only thing I used it for was to play Tetris during my history class. Because I hated my history class.
I was going to use it for the ACT and SAT, but I just gave up.
I got really good at Tetris using that graphing calculator. The really funny thing is that he went on to be a music major. I actually still have my first calculator that my dad ever bought me was an HP scientific calculator from the 80s. And it's still the calculator I use. And it's still a great calculator. That thing roars super fast. But I never owned a graphing calculator and still don't today. Never had a use for me. Although I'll show you my favorite calculator ever. See if I can find it online here. Screen.
It sucks because we did a worksheet in my math class at the end of the year, and it was all physics stuff, and she didn't even hand it back because it was one of the last things we did, so I don't have it.
So here is a great calculator right here. That's not the right one. Shoot.
Yeah, it is.
That's not the right one. Oh, this is it. I love this calculator. I don't know if you can use it from here though. I have it on my...
Oh, it's where you can like draw.
Yeah, you just draw your calculations and it converts them to math. I'll bet you they have this on there. I think I have one of those. I used to have it on my iPad. I can't remember if it's still on here, but I'm sure they do. Yeah, it's on Google Play. Yeah. And it was free, so I assume it still is, but I don't know. It's just a cool it's just one of those cool things to whip out when everybody else is pushing their little buttons. Just say, ah, here it is. And it can do calculus, I think, even if I remember correctly, or maybe that's the pay-only version or something like that. But yeah, it can do some pretty intense stuff. Yeah, it can do sine, it can do factorials, it can do logarithms. And then you can copy things and paste them and save them. And, I mean, it's intense. Yeah. And see, in this one, it's actually saved variables. It saved the variable phi, right? So it can do all kinds of crazy stuff. That's good.
Okay, let's try this again with the right numbers.
Yeah, so here we go. Now we just, what do we do? Do we hit enter? I don't know what we do. But it knows what it is. I think maybe I have to write it here. 0 to 1,000, 15. I don't know how to make it go though.
I think the only thing is the 0 needs to be farther to the left. I don't think it's maybe. I don't know.
No, I think it's good. Anyway, it's a pretty cool calculator. Number 16. Okay, so in this one, that's this one here. You don't need any formulas. Oh, because it does want speeds, right? So in this one, it's all about a very simple equation. It's this one right here. Final velocity equals initial velocity minus v. You're done. And the thing that you want to calculate is this one. So your initial velocity is the one that they give you, 29.4. And then you just keep plugging in different times and calculate. You're done. My scouts are going to Medicine Mountain in a couple weeks here.
Medicine Mountain.
You're wearing a t-shirt from me.
Duh. Sorry, it takes me a minute to figure out what summer camps are. Because
Yeah.
I started out in Troop 291, and I went to BDSR, Ben Bellator Scout Ranch. Then we went to Lewis and Clark. You know Craig Godfrey?
Yeah.
Okay, well, he was our scoutmaster, big guy.
Yeah.
Really heavy camp.
Yeah.
So you can be the math there.
That's the one where you have to park down like 800 feet below the base of the camp or something. You have to hike everything in.
I think so. It could be. No, we were able to drive our stuff in, but
Really?
the problem was like we got the worst campsite. Like we're over here, and then everything's up here.
Yeah.
Or maybe it's over here, but you have to go
Over the
to
top.
get there.
Yeah. Yeah. I've not been to Ben Bill too. I've heard it's good, but I've never been
If you guys are going to Medicine Mountain, this is going to sound really stupid, but have at least 2 or 3 of your guys practice throwing pine cones into a hole about that big.
there. Is that one of the challenges they do there?
They have like this giant relay race that takes you all around the camp.
Yeah.
And we were able to, we had enough staff to put together 2 teams, and both our teams were doing awesome. Like, I just got stuck on a random thing, but I was able to do it really fast. And so I gave him like a 3-4 minute lead. But this guy who's throwing it in there, he like gets a lot of close ones, but he can't get it into the hole. And so that was our problem.
Yeah. I've been up there before. The thing I like best about that camp is there's no mosquitoes. It doesn't really ever get hot, and they have wild raspberries all over the camp. And I love raspberries. What's that?
There's tiny little spaces with numbers.
Oh,
Can't see them.
your screen is just shrunk down. You can make it bigger if you want to. View. Go to Zoom. Do it a couple of times and then
There's one with spaces, so
oh, it's like short.
it's everything, and it's like PG 99 oh, and then mine, that's just it looks like my signature.
I wonder if you reset the page, if it would change it now if you zoomed in. Mine's opened up big, so mine's got some room here.
Yes, I got it right.
Did you get that one right? All right. We're getting pretty close to 6 o'clock. Is there anything else either of you want to talk about here before we're done here?
If I can just ask questions on a couple of the methods.
Okay.
Okay, so on number 16,
Yep.
define the velocity of each point. We would just use kind of the adaptation for velocity. Like, yeah, that one. That's what I was. Okay.
Do we use that for number 18 too? For the velocity?
The velocity part, they want to know the horizontal velocity after 5 seconds. So you can use that one, but you have to realize that, oh man, I just ripped my shirt.
Wouldn't the horizontal velocity be the same?
It's Vx equals V0x plus acceleration times time, and you have to realize that the acceleration in the horizontal direction is 0. So what does this equation really tell you? That it just stays the same, right?
Mhm. So on 18,
Hey, I just got these shorts.
and then on the second part where it says how far will it move horizontally after 2 seconds, you just use one of your equations for distance. Oh, distance
'Cause it's
is
constant.
speed times time.
Yeah, because it's constant, it's just speed times time. Wasn't it nice of me to give you easy ones at the end?
I know.
Or would you have preferred all the hard ones at the end?
No, I want all the easy ones at the end. Orbital motion is another example of projectile motion.
That's 17?
No, that's on number 19.
Did I do a 19? Did I do another orbital motion? Oh gosh, why did I put 2 of those in there?
So is that one we're not supposed to do?
Yeah, that's not right. That's not right.
Okay.
I'll take it out.
And projectile motion has to be something that's moving independent of like being on the ground, right?
Yes, well, it has to be independent of any forces. It has to be,
So like a planet orbiting the sun wouldn't be because it's not independent of forces, right? It's the gravity of the sun.
it has to be independent of any motion that is not gravity.
So a planet orbiting the sun would be or
Let's
it's
take
on
a look.
number 20.
Let's go look at that one again really quick here. Number 20. Indicate which of the following are examples of projectile motion. Soccer ball kicked through the air.
That one I marked because it's,
How about this one?
I wasn't sure about that.
So if a kid's on the water slide and he turns, is that a force that's turning? Is that some kind of acceleration?
Uh-huh.
And is it acceleration because of gravity if he's turning? No, it's acceleration because he's running into the edge of the thing, right? And the edge of the slide pushes him, so that one's not. Falling off the edge of a table,
Yep, that one's projectile.
ball thrown straight upwards,
Yep.
ball rolling down a slope.
I wasn't sure about that one
Is it just free falling?
either. Nope.
It's not.
So,
So the ground, well, friction and the ground is turning it as well because the slope is a slope, you know, and so it's turning, so it's not.
Okay, and then a planet orbiting the sun.
So that's a good question. Let's check. Planet orbiting the sun, soccer ball, a book falling off, ball thrown straight upwards. Let's see. It is. They're counting it as one. Some books would, some books wouldn't, which is why I wanted to check it. But it is a free fall. It's just a free fall in space, right? It has a constant forward motion, and then it has a falling motion, which makes it fall around the sun. The only difference is that its forward motion is not horizontal motion necessarily, unless you consider tangent motion the same thing as horizontal motion, which it is technically, but that's not how we've addressed it before. So you need to just be a little bit careful.
On number 21 here.
Yep.
So that one, at the top of its slide, its velocity is always 0, right?
Upward. Yep.
And then at the top of its acceleration is constant, isn't it?
Yeah. What is the constant
Yeah,
acceleration?
it'd be negative 9.8
Yep.
meters
Yep.
per second squared.
Yep.
And then
Because in projectile motion, your acceleration is always negative 9.8 meters per second squared, right? It's always the same. Never changes. Number 5, aircraft airspeed of 245 kilometers an hour north. Planes roll off velocity across. So this one is the one where we have additive velocities, right? The airspeed. Airspeed means how fast it's moving relative to the air. So it has this 25, in other words, the jet engines are pushing you at 245 kilometers per hour this way. But the wind is pushing the plane this way. East, west, other way. This way. So the wind is pushing it this way at 57 kilometers per hour. And they want to know what is this one here. Right? So you can use Pythagorean's theorem to find this, the length of this, right? Which would be the speed.
That's the nine.
Yeah, this is amended right here because this one's north and this one's west. And then you can use the tangent to calculate the angle right here. Right? If this is your angle theta, which would be west of north, and do they want to know the angle? They actually, oh yeah, they do want to know that. They want to know the direction, but not the angle. You just have to choose the angle. The angle is not necessary, but you do know that it's going north, northwest. Right?
Mr. Gator, just be able to look at number 20, the last one.
Last one, 22.
And then the rest I can probably do that.
So it's thrown through the air at an angle, initial velocity 23 meters per second, or use a separate velocity acceleration behaved during flight.
So horizontal acceleration after it's thrown is 0.
Yep.
Flight, isn't it? And then your vertical acceleration is the 9.8 meters a second.
Yep.
Horizontal velocity always remains constant unless we start factoring air resistance. And then the vertical velocity changes at the rate of gravity.
Yep.
Awesome. I just wanted to make, I wasn't so sure about the horizontal acceleration. I wanted to make sure I had that.
It's 0.
Yep.
Okay.
Okay. Thank you so much.
Yep. Do you have any more questions, Leslie?